Welcome everyone. So in the last class, in the first class, we actually started our discussions about how different fluctuations can be seen if we measure in smaller systems, and we started with how, let's say, a small particles, if it is suspended, let's say a colloidal particle is suspended in a solutions, then we can see that it's some certain physical quantities, they vary with time. And we also see we have also seen that these fluctuations, they are caused by the random thermal motion of molecules which constitute the system. And we also in the discussions that we'll study, we you know set our main goal to study about those fluctuations which are mostly Brownian motion or Brownian motions in shows Brownian motion in nature. And we have seen that Einstein actually showed these relations between microscopic fluctuations at equilibrium to macroscopic response of the system to the external forces, and that is actually called the fluctuation dissipation theorem. And then we studied extensively about time correlation functions, how they are defined, how these time correlation functions are defined. And we defined Brownian motions, and those particles which shows uh, Brownian motions, these are called Brownian particles. And we then tried to calculate time correlation functions, the TCFs. And we you know we wrote down their properties, how they abide by the time translation invariance nature. And also we have also come to the conclusion that autocorrelation function is an even function. And then we also inquired about how time correlation functions, their symmetry properties in unfold. And we have seen and seen the forward and reverse processes. And at the end we studied that dynamics of fluctuations can be characterized either by the deviations time correlation function, or by the correlation of displacement, as they should be related as long as this quantity delta x at initial stage, the deviation of initial quantity, its squared, is finite. Okay. So now we are resuming our today's portion. So now, we sort of seen the position correlations. Now we will see how velocity correlation functions. Velocity correlation functions. Okay. So let's say, x let assume xi, this dot del t, is the time derivative of xi t. That means xi dot t is equal to dxi of t dt, right? Then we shall call this xi t as the velocity velocity of xit, right? Now we will calculate these time correlation functions of this velocity. Now this time correlation function, time correlation function of the velocity xi dot t, this can be obtained from can be obtained from time correlation function of xit. Okay, this can be obtained from here. How? This can be obtained as xi t xj t prime and their velocity like this, and if you take their average, that is as similar to taking this double partial derivative of this thing, right? Because this is actually gives this actually gives this del xit delta x j t prime, okay, and this one. So now what I will do, I will, you know, since it is translational invariant, so I will minus t prime from both ends. So then this term will be delta x I 0, so t minus t prime, and this term will be 0, delta x g 0. So delta 2 delta t prime, this will become delta xi t minus t prime delta xj 0, right? Okay, now if you use it like this, that so now the whole thing becomes like this. Now you can use if t t prime t prime, now this is t minus t prime, so this can be written as minus delta 2 del t2 minus delta xi. So we will see this later how to do this. So this is like this. So xi, then xi t dot xj dot 0, that means if you make it t prime as like this, then it becomes as minus del 2 del t2 del 2 del t2 and delta xi t delta xj 0, right? Okay, now here if you think about it, there is minus t prime, so if you, so this is a variable of t, so you can write here, if this is t minus t prime, then delta del t of this one will be right. It's like the done. But if you with respect, if you derive with respect to delta t prime, then it will be minus delta x t minus t prime, right? So it will be minus t prime. So for that thing, it becomes del 2 minus delta x I t minus t prime delta xj 0. This is number 11. Okay, so this is the equation. Now what you can do, you can get the, you can use the equation 10, this equation, right? Now if you use this equation, then it becomes half del 2 del theta 2 is equal to xit minus xi0, xit minus xi0 into xjt minus xj0. This is this like this is like this, and you are taking the average of this. So we have used here this relation. Okay, so this is sort of making it 0, so this minus and minus cancels out. Okay, so this is by using equation 10. Okay, so this is equation 12. Therefore we can easily say velocity correlation is obtained from displacement correlation. Conversely, you can also say that you can get the displacement. Conversely, you can say the displacement correlation is obtained from the velocity correlation. Okay, by how? By this xi t minus xi 0, this correlations with xj t minus xj 0. So their correlations is equal to, which can be written like this, 0 to t dt1, 0 to t1 dt2 x I t2 dot xj dot 0. Okay, so this is very important because we will calculate few quantities later on using this thing. Okay, so this correlation part is here. We will stop here. Now we will got to know some thing about some noises. Okay. So let's say there are multiple multiple things. So let's say the noise. Let's say noise. So before going into the noise, I think you should talk about first the Brownian motion of a free particle. Then we should go to that. Okay. So let's say we are now calculating the or studying the Brownian motion of a free particle. Okay. So now let consider there is a Brownian motion of a point particle in free space. Okay, and let us assume let first we will talk about only one dimension. Let xt be the x coordinate of the particle position at time t. Okay, now if the particle is macroscopic, if the particle is macroscopic, then the time evolution of this position coordinate should be described by usual, equation of motion of mechanics. The evolution, the evolution of the particle should be described by the usual laws, usual equation of motion, right? Equation of motions. Now, let's say a particle, let's say a particle is moving in a viscous fluid with velocity v is equal to x dot. Okay, is equal to x dot. So if it is moving with a velocity v in a viscous fluid, so there will be some viscous drag. So it experiences a drag, if L, let's say this is FL, or FL, or let's say if it is friction, this is friction also. Let us if from the fluid, okay. Now we know from Stokes equation that for very small velocity, Stokes showed that for small velocity, this FF is proportional to the velocity of the particle. Okay, and this FF, if you talk about this proportional FF, this is equal to gamma V. Okay, and this gamma is called gamma V, where this is 14, and this gamma is called friction constant or drag coefficient, or drag coefficient. Okay. Now, for a spherical particle, we know for a spherical particle, of radius a, this is gamma is given by 6 pi eta a. This is equation 15, where eta is viscosity viscosity of the fluid. So we will show how this is, this is evaluated. This is also a fascinating calculations. So now you got these two equations. So now if got this resistive force, this friction force. So now for a macroscopic free particle, then, so for a macroscopic free particle, the equation of motion, the equation of motion becomes m dv dt is equal to minus gamma v, where m is the mass of the particle. M is mass of the particle. Okay. So now you know this. This is equation 16. Now you can solve it immediately. How to solve it? So this will be dv by v is equal to minus gamma by m dt. Right. Now if you integrate it from v naught to v, dv by v to 0 to t minus gamma by m dt, then you get log v with a limit v naught to v is equal to minus gamma t by m. And from here you can easily write as v minus v naught, v minus, sorry, log of v by v naught is equal to minus gamma t by m. So from here you can write v by v naught is equal to e to the power minus gamma t by m, and from here v is equal to v naught e to the power minus gamma t by m. So now you can see what happens. Mass is very big, so you can write this is as equation 17, and you can introduce a new time scale tau v as m by gamma. Okay. Okay, so now you can easily see that it is speed. So velocity is velocity of the particle falls off exponentially. That means after a certain time, after very rapidly, it will go to zero. But if you see under microscope, these particles actually they are moving. So that means this is not a proper description. This is not a proper description. So we should add, we are missing out on something to incorporate to these things. So equation equation 16 is not appropriate, is not appropriate to describe the motion of small particles. Motion of small particles undergoing Brownian motion. Because due to the above description, this particle should stop after certain time, but in real life we see under microscope that Brownian motion is moving, doesn't stop moving. Okay, so now what we are missing on was, so what did we miss out? Miss out, miss out. So we missed on the fact that we should, so we should have taken into account the fluctuation fluctuations of the forces acting on the particle. So here we missed on something. So we need to remodel it. So the fluid surrounding the particle is made of small particles. So the fluid around the particle and the particle is made of smaller molecules, smaller molecules which collide with the particles which collide with the particles, sorry, which collide with the particle, the single particle we are talking about. So giving randomly fluctuating force. Now this effect, to model this effect can be modeled, can be described, can be described by the following model equation. Model equation which is like this: m dv dt is equals to minus gamma v plus fr t. Let's say this is equation number 19, where this fellow is the fluctuating force exerted on the particle by the fluid that we missed on earlier. So this is the fluctuating force on the particle. Okay. Now I will spend few minutes on this, that how it's important. So let's see. So equation 19 equation 19 is a differential equation, right? Is a differential equation. So which involves stochastic variable effort. And this kind of equation, such an equation is called Langevin. We call Langevin equation or Langevin equation. Now to define this kind of equation, what you need is, now to first we now this contains all the information. This is sort of a phenomenological term. FRT is a phenomenological term to incorporate all the collisional details of the uh, like imparted on the particle. So these Langevin equations, now we need to first to define Langevin equation. Langevin equation we need to specify the statistical property of the stochastic variable. So we should first talk about this stochastic variable, okay, which is none other than this guy, FRT. Okay, so to do this, we will take the help of time correlation of random forces. So now talk about time correlation of random forces. Okay. So now we will talk about, so if we know the properties of random forces, then we can, the statistical properties of random forces, then we can sort of solve or sort of play with the Legendre equations. Now to specify to specify the statistical properties of random force FRT, let us first consider its average. Okay, first consider its average, how it looks like FRT, and B, its time correlation. Okay, which is this denoted by FRT and FRT prime, its correlations. Now I will give you following logics. Following logic. Let's say if something is colliding the other thing randomly, isn't it logical to think that average of this force, since it is a vector quantity, the average of the force is 0? I guess it is logical. So that's why I will write it is natural to assume that the average of the average of the random force is 0. So that is, you can write as average of FRT is equal to 0. Okay. So this condition is necessary for this equation to be valid, equation number 19. So remember this. Equation 20 is a necessary condition for equation 19 to be valid. If it is not satisfied, then obviously equation 19 will give incorrect results, wrong results. Equation 9 gives the incorrect result. That the average velocity Vt of a free particle is non-zero. On the other hand, you know that average velocity of a free particle is not non-zero, is zero. Okay. Now let us understand the time correlation of random forces. Okay. So first, random force FRT arises from the random collision of fluid molecules on the Brownian particle. Since the fluid molecules are thermally energized, so they will collide incessantly with the Brownian particle. So random force FRT arises from random collision random collision random collision of fluid molecules on Brownian particle. Therefore, the correlation of the random forces is expected to decay very quickly. So try to follow what are the logic is being given. So here the random force, it is actually their time correlation is going to be decayed very quickly. That means the correlation time is of the order of a molecular collision time. Molecular collision time. Collision time. That is in the range of picosecond. So pico means 10 to the power minus 12 second. Why is so? What is the molecular collision time? That means, let's say one collision has happened and then next collision happens. In between the time spent by one molecule without any collision. So this is in the range of picosecond. Okay. Therefore, which is very much less than the macroscopic timescales. Okay. So if that is very much less than macroscopic time scale, which is our observation time scale, then we can easily write this as f r t1 f r t2 their average is equal to some coefficient into delta of t1 minus t2. Okay, so I will explain each and every term. So a is a constant, we will determine it later. Okay, now that means this is a delta function. So we can see that it is like delta correlated, right, or uncorrelated. Now to calculate this, we will use the equations to solve it. Okay, so let's start then. So now here, to determine a, we calculate v of t whole square and its average by equation 6.19. Okay, so the equation 19 probably, and use the condition, and we will use the the condition that it must be it must be equal to kBt by m at equilibrium. So this is the first thing we started with. Okay. So now if you solve this equation, then how do you write it? Hmm. So your equation becomes here m dv dt is equal to minus gamma v plus f r t. From here you can write, so if you, so this integrating factor, if you get this integrating factor, then it becomes, so from the partial equations we can write easily v of t is equal to v naught e to the power minus t by tau v plus, so this is the integrating factor, so the integrated factor will be plus of this, so this will be 1 by m, and starting from minus infinity to t, and it should be by this, right? And for this term it will be e to the power e to the power let me write it here, this will be e to the power minus t by tau v, this is minus infinity to t, this is dt1 e to the power t1 by tv fr t1, right? Or we can easily write this as v naught e to the power minus t by tau v plus 1 by m minus infinity to t dt1 e to the power minus t minus t1 by tau v fr t1. So this is equation 22. Now to calculate Vt square, so now to calculate V of t whole square and its average, what we will do these things multiple times, and this term will be 0 because this is exponentially falling off. So if you Vt square, then this term belongs become 1 by m squared, and then average first minus infinity to t, first this is dt1 e to the power minus t minus t1 by tau v fr t1 times minus infinity to t dt2 e to the power minus t minus t2 by tau v fr t2. Okay, Then it is become 1 by m square minus, so that we can take this average inside this. So this becomes minus infinity to t dt1, and again minus infinity to t dt2 e to the power minus t minus t1 tau v to the power minus t minus t2 tau v, then is equal to fr t1 fr t2. Now this term we know, right? What is this value? This is a delta t1 minus t2. So now we will substitute this value, then it becomes, this is equation number 23, then it becomes 1 by m square minus infinity t dt1 minus infinity t dt2 e to the power minus t minus t1 tau v to the power minus t minus t2 tau v a delta t1 minus t2. Now when, let's say, if you integrate with respect to t2, this means these functions will be t2, every time t2 will be replaced by t1. So then this term becomes 1 by m square minus infinity t dt1. So first term will be as usual there. So this is e to the power minus t minus t1 by tau v, and here, so since this is the delta function, so this will be there. So t2 will be replaced by t1. So then this becomes t minus t1 divided tau v times a. Okay, because you know, for us, for a direct delta function, this is the property. Clear? Now if this is the case, then you can easily write this as 1 by m squared, sorry, a by m squared minus infinity to t dt1 e to the power minus 2 t minus t1 tau v, right? Now what will be this integration? This is e to the power minus this thing, so this will be a tau v by 2m squared into e to the power minus 2t minus t1 by tau v. Here the limit will be minus infinity to t. Okay, so if it is t, then it is 0, that means 1. So a tau v by 2m squared, first is 1, and for minus infinity this will be plus plus 2t1 means 2 infinity. So minus, this will be minus infinity, so this will be 0. So then it becomes a tau v divided by 2m square, right? Now we told you guys that after calculating Vt square average, we will be equaling it with kBt by m. So now if you equal it, so through the relation, through the relation we can write Vt square average as kBt by m, which is equal to a tau v by 2m square. So from here we can easily write, equaling this thing, that a must be equal to 2m 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 kBt. Yes, a must be 2m kBt divided by tau v, right? So now from here you can write here that a is equal to tau v was m by gamma. Tau v was m by gamma. So now if you substitute this value, 2m kBt by m by gamma, then it becomes a is equal to 2 gamma kBt. So this was this thing. So therefore we can easily write, therefore it readily becomes, therefore it becomes if r t1 if r t2 is equal to 2 gamma kBt into delta t1 minus t2. So this is the complete time correlation function relation of this noise. So now we can discuss the following things. So equation 26, what it indicates, what does it indicate is that fluctuations, the fluctuations of the forces exerted on the particle, on the particle by the fluid, by the fluid are expressed by three single parameter. by gamma, which is the parameter parameter represents dissipative force of the fluid, dissipative force exerted by the fluid on this particle, and okay. So now you can see the fluctuation of the forces are sort of related to the dissipations. So here you can easily, if I, the fluctuation of the forces are expressed by the dissipative force exerted by the fluid. This relation exists generally. Such a relation exists exists generally and is called fluctuation dissipation relation. And this is a key concept for these relations. Okay, so just a minute, just take 1 minute break. So what we have found here is the fluctuation relation, fluctuation dissipation. Fluctuation dissipation relation. So first, there is also some interesting discussions to be done for this thing. Is first, if you have noticed this time correlation relation does not involve the mass of the particle. So this this time correlation function TCF of f r t is independent independent of particle mass. Okay. So you can say this is reasonable because this random collisions, this random fluctuating force actually determined by the fluid molecules. There is no role of this uh, this single Brownian particle. So so this is quite logical. This is quite logical since FRT is determined by the fluid molecules alone, and thus its statistical properties should also be independent of the mass of the particle, right? Thus its statistical properties should be independent of the mass of the particle. Now, so this is on relations. Also, the statistical properties are not sufficient to specify the statistical properties of random force completely. So this is time correlation, and this is the average. So these two, so the average and time correlation functions, that is equation 20 and 26, they are not sufficient to specify the statistical properties of the random forces completely, because average will give you the first moment, and from time correlation functions you will get the second moment. Okay. Now for a complete specification, for a complete specifications specifications we have to make we have to make further assumptions. It is said that since since the the random force is a sum of forces exerted by many fluid molecules many fluid molecules molecules near the particle. Its distribution is expected to be Gaussian. This is because I will talk about later. So therefore therefore we may assume that if RT, this random noise or random force, is a Gaussian random variable, variable whose mean and variances variances are given by given by 6.20, given by equation 20 and 26. And with this it completes the specification of FRT, and that it defines Langevin equation. Now star means this means this is the result of result of central limit theorem that we will discuss later in our discussions. Okay, so this is mainly this thing, so we'll discuss later about those things in great detail. So that completes this completes the specifications of this random force FRT, this random force, and defines the Langevin equation. Okay. Okay, so we will stop here. We will resume our classes in the next time.